Howdy! This is your friendly neighborhood physics teacher here, and we're going to talk about momentum and impulse. Mainly, we're going to talk about conceptual questions. These are the ranking questions that you've seen on tests and everything. So we're going to talk about those. Let's just go ahead and jump right into it. Basically, this PowerPoint is up on Schoology for you. I'm going to do the first 8, and then I'm going to put the other 8 that are on the PowerPoint into a assignment for you to sit there and do and check. The other assignments I am finishing up checking, and then I'll also give you a second try for those assignments. The first assignment I can't make comments on. The ones you're supposed to take notes, so I might make a video just going over those and then giving you a second. But on the other one that I did on Friday, I can make comments on those. So I'll make comments that you can check and see, and then I'll give you a second try on those homeworks. So be looking for that. And don't forget, you do have the AP College Board questions online. I'm probably going to give you tomorrow, so I won't necessarily post anything for that one. But I'll give you a chance to work on those, and then I will work on the free response. I'll make a video over the free response since those tend to be hard, and then I'll look to see all the which questions were the most missed. I'll make a video over the most missed questions. So that thinks about how it's going to look for the next week or so. So let's get on to it. So in the figure below, balls are traveling in different directions. Balls have the same size and shape, but they are different masses and are traveling at different velocities as shown. Rank the magnitude of the momentum. So first thing, let's do the equation for momentum. Momentum is mass times velocity. So with mass times velocity, P is your momentum, mass times velocity. Now the key thing in here is magnitude. Magnitude just means number. So even though they're going in different directions, and so this velocity would be positive, this velocity would be negative, this velocity would be positive, this velocity would be positive, does that really matter with magnitude? Hopefully you said no. So we have a video. So we have our equation, and we have what's going on. So we're just going to take our mass times our velocity. So we have 8. I'll just plug that into your handy dandy calculator. Just do 8 times 3, and you get a 24 momentum. The same thing, you'll just go 2 times 7 to 14. Now, that negative doesn't matter because it's just talking about magnitude. You're just talking about the number. You're not talking about the direction. So 5 times 3 is 15, and then 2 times 7, again, is 14. So now we just got to rank them. So it goes greatest to least. So the greatest would be A. The next one would be C. And then your B and D are equal. So there we go. So B says rank the kinetic energy. If you remember, your kinetic energy equation is 1/2 mv squared. So again, we have a mass and velocity, so you're literally just plugging in 1/2 times 8 times 3 squared. Do not forget about that squared. Remember, we tend to forget that. So don't forget about the squared. So A is 36. So 1/2 times 2 times 7 squared, 48. Now, what if you do a negative? So if I did 0.5 times 2 times negative 7 squared, does that change my answer? No, it doesn't, because your energy actually is a scalar, and it does that, again, because of that squared aspect there. Now we're just going to do 1/2 times 5 times 3 squared. So that gives you a 22.5. And then a 1/2 times 2 times 7 squared gives you a 49 again. Again, so we're going to do greatest to least. So the greatest would be B and D. And again, it doesn't matter which direction it's going. It has the greatest kinetic energy. And then it will be A, and then B. And if you notice, yeah, so the one that had the least amount of momentum has the greatest amount of kinetic energy. So yeah, there we go. So let's go on to the next slide. So identical boxes that are filled with different amounts of sand are initially at rest. A horizontal force is applied and the box moves across the floor. The mass of the box with its content and the net force acting on the box while the horizontal force is applying is given in each figure. Rank the magnitude of the impulse on each box for a 2-second time interval. So your impulse equation is force times time. That's what impulse is. So do you see mass in that equation at all? Nope. So mass doesn't matter. So your mass doesn't matter. We're just looking at force and we're just looking at time. Now our time does not change. So that is our t no matter what. So honestly, you don't have to do any math for this one. You're just looking at which one has the great amount of force. So the great amount of force is D. Then it'll be A, B, and then it'd be equal, and then it'll be C. So there you go. Just understanding the relationship as the force. Because if our time stays the same, but our force increases, our impulse has to increase. Okay. So again, same exact setup, but in this case, we're asking for the change in momentum. So we have two equations that we can look at. Our change momentum equals mass times change velocity. But change momentum can also equal our impulse, which is force times time. So either one we can look at. So let's see what we got. So it says, what is magnitude? So again, the word magnitude, does direction matter? Nope, no direction. So for the change in momentum, for each box for the same time interval. So again, our time interval is the same. So t does not change. And we're looking for our change in momentum. If we're looking at this equation over here, do we have velocity? Nope. So that means we can't use that equation because we don't have velocity. We have our time. We know our time doesn't change. We have our force. So again, we're just looking at how force affects our time. So this one's kind of easy. You're just seeing which one has the greater force. Again, mass doesn't matter. So it would be AD equaling to each other, and this would be BC equaling to each other. And it's because mass doesn't play a part. Mass doesn't matter. Now, if we're looking for the change in velocity or something, yeah, that's when mass starts mattering. But since our change in momentum is just force times time, that's all we got. So a car moving along horizontal roads are about to be stopped when they hit a protective barrier. All of the cars are the same size and shape. Same size and shape, but they are moving at different speeds with different masses. The barrier are all identical and exert the same force. So this is right here is saying it's all the same force. Rank the time, so we're looking for time, that it takes to stop the car as the barrier applying the same contact force. So we're given velocity, we're given mass, we know it's the same force, and we're looking for time. So that's when we do the mass change velocity equals force times time. So the first thing we need to do is figure out our change velocity. So remember, change velocity is final minus initial. Except y'all don't really write it that way. Stuck in pre-AP world here, right? So final minus initial. So final, so this would be our initial velocities for everything. What would be our final velocity for everything? So our final velocities would be 0. The reason our final velocities will be 0 is because it's hitting the wall. It's stopping. So all of these will end up having a negative velocity. We'll end up having a negative velocity. Because final is 0, because you have a 0 minus insert number here, like 10, and it'd be a negative 10. So your change velocity ends up being negative. Because the wall's slowing it down. That's one way to think about it. Yeah, so we're looking at this equation up here. I'll kind of write down one real quick. So we have our mass equals our change velocity, whoops, not equals, times our change velocity, which would be a negative 10, equals, so it exerts the same amount of force. In this case, it is a negative force because it's, remember, we kind of talked about, is it a positive action or a negative reaction? So it would be a negative force because it's slowing it down times our time. Now, it doesn't give us a force, right? It just says it's the same. So make up a force. It doesn't matter as long as you use the exact same number. If you really want to use number-wise. So let's make it easy and let's use 10. So we're just trying to find our time. So our time ends up equaling, that ends up canceling out, our time ends up equaling 3,000 seconds. And you sit there and just do that for each one. So this is 3,000. So you can just do that for each situation. And again, as long as you leave the force the same. So in step 1, or the second one, you have 1,000, negative 20, because remember it's slowing it down. So negative 10, and we're looking for time. And so you get your time to be we get our time to be 2,000 in this case. And then you work it again. So it's just, so you just had to figure out that since your force is the same, you could sit there and figure it out mathematically that way. So yeah, we just keep doing it. So we have 1,000, negative 30 equals negative 10. Again, what you do to one side, you got to do the other. Now remember that negative 10 we just made up. We just made up a force because it's the same. So it doesn't, if you don't want to use 10, use 5. It doesn't matter what you use as long as it's the same. So honestly, we can keep that side the same. So we have 2,000, negative 20. And this got 4,000. So we can rank it. So the most time it took would be D. The next one, we have a tie for A and C. And then we have B. Now, this is just a side question. Do you want there to be a short amount of time or a long amount of time when you're hitting a wall? That sounds bad. When you're hitting something. Hopefully you said long, because the longer it is that when you come in contact, the more that force is spread over a certain amount of time. So you increase the time, you decrease the force. So we want that long length of time there. Okay, so let's try another one. So an object changes its velocity as force acts on it for 5 seconds in various ways shown below. It gives you all the different ways. So for the question below, use the directions indicated by the arrows in the direction roster, or use J for no direction. Identify the closest directional match for the direction of the impulse on the ball for these cases. Explain your answer. Okay, so let's look at the first one. So we're saying the direction of the impulse. So it changes direction. So it's going, so like for part A, it's going, a ball is going 3 meters per second to the right. 5 seconds later, so like after it hits a wall, it's going 7 meters per second to the left. So we have that change in velocity. And it's asking for indicate the closest directional match for the direction of the impulse on the ball of these cases. So basically, which direction did it have to be hit for it to change? Basically, that's what it's saying. So A should be pretty easy. If it's going to the right and all of a sudden it's going to the left, think about baseball, you hit it to the left. For B, it's going to the right and all of a sudden it creases to the right. You're adding it, you're hitting to the right. So if it's going to the right and all of a sudden now it's going up, so that's a complete change in direction. And that's when it's getting kind of tricky because it can't just be up, because then it'd be going at an angle, right? Because so think about triangle wise. So if it's going that and we hit it just up, it's going to be going that way. That will be our resultant. So we have to think about which direction we hit it so the result is straight up. So if it's heading this way and we want this, we want that to be our resultant, that kind of gives us this. This has to be our answer. So C, you got to hit it that way. And kind of the same thing, we're wanting that to be our resultant, then we got to hit it that way. So you're kind of thinking backwards for C and D. But yeah, there we go. Oh, and so I guess this would be S. Should have put an S, an O, a N, and a P. So there we go. So cars are cars with spring plungers run into fixed barriers. The cars are identical but are carrying different loads and have different masses. The velocity of each car just below and just before and just after impact is given. Rank again, we have the magnitude, so does direction matter? No. Change momentum of the carts. So again, we have two equations for change momentum. We have mass is change velocity, or we have our impulse to be force times time. Now the information it gave us, it's giving us mass and it's giving us velocity. So we don't need that one. So we need to figure out the change velocity first. So we need to figure out the change velocity. Remember, your change velocity is just your final minus your initial. So it would just be 3 minus negative 3. So your change velocity in this case would be 6. This would be 0 minus 2. So your change of velocity would be negative 2. This would be 1 minus 1. So your change velocity would be 0. Wait, nope. 1 minus negative 1 would be 2. Fun stuff. Need to wake up. Would be 2. That should be a positive 2, not a negative 2. Negatives are evil. Can't forget about negatives. So, and then you have a 1 minus a negative 1 again. So our change velocity should be 2. There we go. So we have our change velocity. And we have our mass. So you just do mass times change velocity. So your momentum would be 60, 20, 20, 20. So yeah. So all of them are almost the same, except did I mess up on this negative one? Hold on. 3 minus a negative. Nope, I didn't. Just making sure I didn't mess up. So yeah, so there we go. So you have a greatest, which would be A, and then B, C, and D are all equal. That's a tricky one. That's a tricky one. So yep, there we go. Let's go to the next one. So again, we have the same kind of situation. It says, is the direction of the change of momentum in case A to the left or to the right? If the change momentum cannot be determined, state the implication. So we're just looking at this situation. So again, so our change momentum is mass times change velocity, because there's no force in time, so I don't need to worry about the other one. So the first thing we need to figure out is our change velocity. Remember, it's final minus initial. So it'd be 0 minus 4. So our change velocity is negative 4. And so you just do 10 minus negative 4, which your change momentum would just be your negative 40. So is it to the left or to the right? Negative means left, so the answer is left. To the left, to the left, to the left. There you go. Which makes sense, because if it's moving and then it stops, the force that had to impact it would be to the left. So before and after shots of a car's velocity are shown. All cars have the same mass. Rank the magnitude of the change momentum of the car. So again, so we're looking at change momentum. We have mass, we have velocity. So you're seeing kind of like a broken record. I'm going to leave this one. I'm going to leave this one for y'all to do. Yep. I'm going to leave this one for y'all to do. Let's see here real quick. What slide are we on? I think I've done enough. So I'm going to leave this one for y'all to do. Let me scroll and see if there's any crazy ones that I might want to do with y'all real quick. So a 2 kilogram object accelerates as a net external force is applied to it. During a 5-second interval that the force is applied, the object's velocity changes from 3 meters per second to the right to 7 meters per second to the left. So this is kind of like the other one we did just for the part 1. So several students discuss the impulse on this object. So you're asking, so this is like, which one do you agree with? So we have one that says the impulse is equal to the change momentum, which is, gives you that. Now remember, I'm kind of give you a hint. Your change momentum is mass times change velocity, or your impulse, which is force times time. But the change in velocity is 4 meters per second, and don't forget your equation for change velocity is velocity minus your initial velocity. We multiply by the mass to get the change momentum and also the impulse, which gives you the answer. And then the change momentum of this object during these 5 seconds was 8. So the impulse implied to this object during these 5 seconds is 8 divided by 5. It says the impulse is the force times the time. And since we don't know the force, we can't find the impulse of this situation. So hopefully I gave you enough little hints on this one. We have a 10 kilogram box initially at rest, moves along a frictionless horizontal surface. A horizontal force to the right is applied to the box. The magnitude, again, does direction matter? No. The magnitude of the force changes as the function of time as shown. So we have force divided by time here. Force over time. A student calculates that the impulse applied by the force during the first 2 seconds is 4 Newton seconds, and that the impulse applied during the following 3 seconds is 6 Newton seconds. What if anything is wrong with these calculations? If something is wrong, identify it and explain how to correct it. If the calculations are correct, explain why. So remember, your impulse is force times time, okay? So force times time. Yep. So don't forget about that. Now, another thing to hint at, when you're doing this, you end up doing, like if you do, your slope is actually force divided by time. And the force times time, remember, is like area under the curve. So hopefully that'll give you enough hints on that one. Oops, nope. Okay, 2 skaters, a large girl and a small boy, are initially standing face to face, but then push off of each other. After they are no longer touching, the boy has more kinetic energy than the girl. A physics student who is watching makes the following connection about the forces that the boy and the girl exert on each other. Since the boy has more kinetic energy, he also has more momentum. So the girl had to have pushed harder on him than he pushed on her. Again, this is you're making a statement. Is it correct or is it not? So a couple of things to remember. Don't forget about Newton's laws. So think about Newton's laws on this one. And think about the first one I did. Just because it has more momentum, does it always have to have more kinetic energy? Do those really go hand in hand? So scroll back through the beginning of the PowerPoint, and you can remember that. So those are my 2 hints on that one. 2 boxes are tied together by a string and are sitting at rest on a frictionless surface. Between the 2 boxes is a massless compressed spring. The string tying the 2 boxes together is cut and the string expands, pushing the box apart. The box on the left has 4 times the mass of the box on the right. After the string is cut, the boxes lose contact with the spring. Will the magnitude of the momentum of the boxes on the left be greater, less than, or equal to the magnitude of the box on the right? Explain your answer. So a couple of things. Remember the Newton's laws, and remember the conservation of momentum law. At the instant after the string is cut, that the boxes lose contact with the string, will the speed of the box on the left be greater, less than, or equal to the speed of the box on the right? So again, remember your change momentum is mass times velocity. In this case, your initial velocity would be 0. So the first one is talking about momentum itself. The second question is talking about speed. Remember, that's just your v. Okay, so I believe that will give you hints on that one. A student observing a rubber ball hitting a wall and rebounding states, a change momentum for the ball is equal and opposite to the change momentum for the wall, because in this situation, momentum has to be conserved. So again, so you have to think about your change momentum is mass times change velocity. The mass of the ball is not changing, so we have to think about what's changing. So hopefully that will help with that one. I think I should be almost done. Two cars are traveling in opposite directions, are about to collide. The carts are all identical in size and shape, but they carry different loads and are traveling in different speeds. The cart sticks together after the collision. There is no friction between the cart and the ground. Rank the speeds of the two cart systems after the collision. So when they stick together. So you're going to end up using this equation. Your mass times velocity plus mass times velocity equals your mass 1 plus mass 2 times your velocity. So this is mass 2, and then this would be initial, and this would be your final. So you're looking for that. So it's asking for, so basically what you're looking for is that. So, and I'll let you do that. How many more do we got? 2 more to do. So again, it's dealing with the collision part and asking which ones are for students' situation of the following. So after the collision, the carts will stick together and move to the left. They will stick together, going to be at rest. Must have the same mission after the collision. So again, so you're just thinking about your momentum 1, momentum 2. So I feel like you make this 1, make this 2 equals, and then if they stick together, you're going to be doing that. And then it's kind of like the same thing. This is a ballistic question, which I have a cool lab for y'all to watch for this one. Again, y'all are just using this equation. If y'all have any questions, please let me know. I'll get these questions posted for you to do. And hopefully the video has helped and you have an awesome day. Bye.